The next talk is going to be by Professor Indumathi.
Yeah. Good morning, everybody. There are some students in other classrooms. We apologize, we could not accommodate all of you in this main auditorium. So I'm not sure if there's a mechanism for those students to ask questions. So if those students have any questions to ask, I'll be there outside at any time. I think you know where the registration desk was. I'll be very happy to answer any more questions. So with apologies to them. I'd also like to know, there's such a mixed audience, I'm not sure whom to aim my talk at. How many of you are not in 8th standard, for example? Can you please put up your hands? 8th standard students, please put up your hands. Okay, very good. Is there anyone who's not yet in 8th standard? Who's 7th and below? 7th, 6th standards, please put up your hands. So let me try to make this talk so that at least 8th standard students will be able to understand it. And some 7th and 6th standard and 5th standard students have put up their hands. Please feel free to ask questions. Let me see if I can give you approximate answers. And obviously the audience who is college and above, I am not really aiming at you. So let me compromise by doing one thing. Half an hour, I have 45 minutes to talk. For half an hour, I will try to talk to the school students. And then in the last 15 minutes, I was asked to talk about the Higgs boson. So in the last 15 minutes, I will talk about the Higgs boson in a very approximate fashion. Is that all right? All right, okay. Now I want to hear some words from you. How many of you have heard about atoms? How many of you have heard about atoms? How many of you don't know that atoms exist? Actually, I would like the lights on while I'm talking so that I can see this audience, otherwise I can't see the audience. So what is an atom? Lights on, please, lights podringla. So what would you say is an atom? Okay, let me pause there. This is the beginning point. How many of you have not heard about atoms? Please raise your hands. It doesn't matter. See, this is no pass, fail, exam, test, nothing. I just want to know where to begin. If you have not heard what an atom is, please raise your hands. Yeah. Theriyada? Theriyuvana kai keele vaingo, huh? Okay, fine, good. So that's a starting point. So we say this is a piece of matter, and if I chop up this piece of matter and I chop it further and further, by the way, in this talk, because I'm going to, kind of address it to so many students from so many different backgrounds, I am going to tell lies, which means that I am going to approximate the truth in very different ways. So the first way I approximate the truth is by saying, what is an atom? Would someone like to tell me what is an atom? Yeah, stand up and tell me. It is the smallest indivisible part of? Particle. It is the smallest indivisible particle. Okay, fine. So what is an atom made of? Does anyone know? Tell me. No, molecules are made up of atoms, correct. But what is an atom made of? One of you, yeah. Okay, fine. Does everybody know that atoms are made up of protons, neutrons and electrons? But then atoms are indivisible. Who's telling lies here? If it is indivisible, it cannot be made up of anything, right? So we will continue to lie like this. So what is the meaning of lies? At some level, when you are in a smaller class, you are told that I keep chopping it till I can't chop it further. This is an atom. This is the indivisible element of which, say, my pointer is made, right? But then people found that you can actually chop up an atom, except it doesn't have that atomic property anymore. Can anyone name any two atoms? What is this atom I'm breathing? I'm breathing only oxygen, 2 atoms. Nitrogen, very nice. So what's in the air? Mostly nitrogen, right? So when I take a breath, I also breathe in nitrogen. So those are molecules, as she said, but they are made up of atoms called nitrogen, oxygen, whatever. And if I chop up this oxygen atom, it doesn't have the property of an oxygen atom anymore. So this is the meaning of saying that atom is indivisible. Is this clear to everybody? Very good. So now we go to what is inside an atom. So what is inside an atom? Once you chop it up, you can chop it up. But if I chop it up, it's that oxygen is not going to remain oxygen. So keep that in your mind. It turns out that there is a central nucleus. All of us are from Tamil Nadu. You've been listening to, we're having a new nuclear power station in Kudankulam, and it's been in the press all the time. We want it, we don't want it. And how do I understand that? I take the simplest possible atom. What is the simplest possible atom? Can anyone tell me what is the simplest possible atom? Hydrogen. Wow, you're all very smart. Why is hydrogen the simplest atom? It has one proton, right, which is the nucleus. I gave the answer because it looks like everyone knows it. It has one proton in the center and one electron going around it. And we know that there is a charge of the proton and electron. The charge of the electron is negative and the charge of the proton is positive. And so what is the charge of the atom? Neutral. Are you very sure? Yes. Exactly neutral? If the atom had not been exactly neutral, suppose a small 0.0000001 leftover charge was there, what would happen? Can anyone tell me what will happen? Yeah, please tell me, the one in the blue shirt, yeah? So it will form bonds with other atoms and what will happen? Think of a physical thing. Can you sit next to each other like this? If you have a remaining negative charge and you have a remaining negative charge, what will happen to two negative charges when they sit next to each other? So no one will be sitting in this room, they'll all be driven away from each other, right? So we know that the atom is neutral to 0, 0, 0, 0, 0, and please look up how many zeros there is. Many, many, many zeros, more than I can tell you now, okay, or keep count of. So the atom is almost exactly electrically neutral. It's a very important point to keep track of. And what keeps the proton and electron together is the electric force between a positively charged proton and a negatively charged electron. Is this clear to everybody? And what happens? Suppose I say that these atoms are very small, right? No one has seen an atom. You've only seen, if the senior students might have looked and seen cells inside the microscope, right? It's called microscope because you can see sizes of order 1 micron. 1 micron is 1 micrometer. That is 1 by 10 lakh of a meter, right? 10 lakh, yeah. That's 10 power 6 if you know scientific notation, right? So very, very small quantities, but the atom is even smaller. When cells are 1 micrometer, that is 6 zeros followed by 1 after a decimal place, the atom is 10 zeros followed by a 1. That means 10 power minus 10 of a meter. So about 10,000 times smaller than cells. They are very small. No one has seen them directly except we infer them through equivalent experiments. Just like you see through a microscope, there is some other instrument which tells you that these atoms are there, okay? But not only the atom is small, the nucleus is even smaller. The nucleus is 100,000 times smaller than the atom itself. And the way to understand it is like this. Suppose I blow up the size of this, you can always make, in a Xerox you can make things bigger and bigger and bigger. Suppose I make the nucleus, the hydrogen atom very big so that the nucleus fills this room. This room is about 10 meters in size, okay? Suppose I say that the proton is the size of this room, okay? Where will its electron be? The hydrogen atom has 1 proton and 1 electron, right? So it has to be 100,000 times farther away. Is this question clear? Suppose I blow up the size of the atom so that we can understand really what this object looks like, make it more like the sizes of the physical world. I make the new proton the size of this room. Where will its electron be? Can anyone guess? How far away is the electron? Will it be somewhere near Meenabakam airport? Closer? Farther? Is it closer than the airport or will it be farther than the airport? Farther. Where will it be? Farther than where? Approximately? Outside Chennai or inside Chennai? Very good. So actually it will be somewhere near Bombay. It will be 1,000 kilometers away. Because if this room is 10 meters, 100,000 times this size is about 1,000 kilometers. Please think of the math, do it in your little notebook, be sure of the answer. So that means the atom is so hollow. If the hydrogen atom, the proton was the size of this room, its electron, the one that it bonds to, the one that it knows as its own, is sitting in Bombay. And what is in between? Nothing. Nothing. It is completely hollow, right? This is again a lie, but for your, at this level, this is completely perfectly alright to understand. And when you go to college and learn about, or maybe in +2 nowadays you learn about orbitals, you'll know why this is a lie. All these lies are half truths, okay? But just because there are some older people, I don't want to leave the lie as it is, so, okay? Fine. So now we understand that there are electromagnetic interactions, and the way that electromagnetic interactions go are of the order of these sizes, which are atomic sizes. So what I want to now tell you, what the world is made of, how the world is made up, the way it is made up, the universe, the way we see it today, is a consequence of such interactions. So now we just saw there are electric forces between the proton and the electron. They cause an interaction between the proton and the electron, and the physical consequence, as a consequence of the electron and proton interacting by electric interactions, it formed an atom. And all forces in nature, every force that we know of, and I'll tell you what these forces are made up of such interactions. Is this point clear? This is what we call the paradigm of particle physics. When we talk about what particles are that make up the universe, this is our fundamental belief. And why is it our fundamental belief? Because we don't know how else to address this issue. Okay? So, this is what I'm going to say now. I'm not even sure that I want to. Okay, can you dim the lights please for now? See, this talk was written with some audience in mind, so I'm only going to pick up a few things and I'm going to talk more, okay? So I want you to look at this little table, what I called an electromagnetic interaction. Okay, forget this, makes electrons and protons interact. This is the matter that interacts, and the physical consequence, as I said, is that atom is formed. This is what we just discussed, right? It turns out that there are many more particles in nature, and maybe I will list them later, what we know and what we don't know. But the funny thing about it is, how does this, so let us think of our blown up model of the atom. How does this proton which is sitting inside this room know that it has to interact with an electron in Bombay? So far away, right? Even when you compress it back down to its normal atomic size, it is still so far away. How is this message sent across that, hey, I'm interacting with you, you better bond with me? This information is sent across by a mediator. That's how you do, right? If you can't go somewhere, you send a friend or you send a messenger, right? This messenger in electric forces is called a photon. A photon is nothing but a particle of light. Light, as this room is in darkness now, so when your lights are turned on, the reason you can see very well is because all the photons are coming at you from the light source. So what you know about as light, I think even 7th and 6th standard, you know what light is. Light travels in straight lines, all those rays undergoes reflection, refraction, right? That same light particle actually has a very, very big role to play at a very fundamental level. And this fundamental level is, when you look at it at the small atomic scale, it is not this friendly light particle which is reaching us from here, but it is doing a very important job, not just lighting up our notebooks or our lives, but causing the interaction to be exchanged or the information to be exchanged between this electron and proton. So the second fundamental component of particle physics is, what are the fundamental particles, and what the second part is, what causes them to interact the way they do. So just you have particles, that's not good enough. What makes them interact is that it exchanges a photon, and this photon exchange between them, it goes up and down, up and down, up and down, and says, yes, you know, you belong to my nucleus, or you are this nucleus is mine, or this, we two together are an atom, kind of thing. Okay, so this is the interaction. So it turns out in nature that there are 4 different types of interactions. The last one, I think all of you know, right? What is the last one? Can anyone read it out? Gravity. Who has not heard of gravity? Okay, I'm happy to hear that everyone has heard about gravity. What do you know about gravity? Do you know any scientist's name with respect to gravity? Okay, Newton, apple fell on his head. And do you know the joke that it was discovered in Kerala, except that it was a coconut which fell on his head? Okay, fine. Okay, so here, what does gravity act on? Answer is here. This is not a test. All matter in the universe, okay? So it's incredible. And the absolutely most incredible thing about gravity, in my opinion, is that it is always an attractive force. No one tells you this in school, but they tell you that like signs repel, unlike signs attract, right? Positive and negative charge will attract, right? But 2 negative charges, you all knew, repel each other. But there are no masses in the universe, because gravity interacts, 2 masses interact through gravitational interaction, right? But no 2 masses ever repel each other under gravity. It is always an attractive force. This is what holds our universe together. The forces between any matter in the universe, therefore the physical consequence of gravity is actually the formation of the universe itself. This is such a profound result, right? That our universe as we see it is held together really by the forces of gravity. This is such an important thing that, apart from making apples fall on Newton's head, it also causes the entire universe to hold together, right? The other two forces are some things that you will learn about only in college and maybe in, MSc rather than even in BSc. So I will just tell you briefly what it contains, okay? Now we said that atoms were indivisible. Then we said that's a lie, atoms are divisible, there's a nucleus, and then there are, okay, maybe it is a good reminder that if anyone has a cell phone, either you switch it off or you keep it in silent, because nothing irritates me more than a cell phone sound, okay? Thank you. So where was I? Okay, so we said there are protons and neutrons inside the nucleus and electrons outside, right? Now the second thing comes that actually these protons and neutrons are also not indivisible. You can chop them up also, okay? So you can chop them up into smaller pieces, and these pieces are called quarks. Very funny name, Quarks. So if I take an electron, I can't chop it up anymore, okay? So far we have tried. Doesn't mean that electron cannot be chopped up. It just means that scientists so far have not managed to chop it up further. So we think that it's an elementary or a fundamental particle, okay? On the other hand, if you take a proton or a neutron and chop it up, you will get quarks, okay? So what is therefore now our understanding of what matter is made up of? Instead of protons, neutrons in the nucleus and electrons going around, we say there are quarks inside the nucleus and electrons going around. I hope this concept is clear to everybody, new, but still just a next level definition of what matter is composed of. So what happens is that you ask this question, now these quarks are actually charged. Some of them have plus charge, some of them have minus charge. But you ask this question, I had hydrogen atom, it had one proton, right? If I even go to the next atom, I don't know whether anyone knows, it's helium. Helium, excellent, helium which has two protons. The two protons should have repelled each other, right? You should never ever be able to form an atom with two protons, because how will they sit in the nucleus? I told you how compressed the nucleus was. They should have just flown apart, right? Two positive charges. How are they sitting inside? That means there must be some other force of interaction which holds these protons together, which is stronger than the electric repulsion. Isn't this clear? Isn't this logical? And you can see that in the helium there is not only two protons but something else. Very nice. There are also two neutrons. Neutrons are neutral objects. I don't have it on the slide, sorry. But neutrons have no net charge, though they are also made up of quarks, okay? But they have strong interaction. So this is the strong interaction, okay? So what happens is that the strong interaction, which is attractive at these small distances, overcomes the repulsion because of the protons all having the same charge. In fact, those of you, some of your older students over here who have seen the atomic table will see that in the periodic table, when you go to heavier and heavier nuclei, you have more and more excess neutrons. Light nuclei, you have 2 protons, 2 neutrons. In carbon, 6 protons, 6 neutrons and so on. But when you go to, even like iron will have 26 protons but 30 neutrons. You must keep adding more and more and more neutrons to overcome the repulsion between the positively charged protons. And this interaction, the strong interaction which binds the quarks into the neutrons and protons is called, because it's a strong interaction, the name itself is called strong force. And how do they talk to each other? Just like the photon is the mediator for the electromagnetic force, the mediator for quarks is called gluons. So they exchange gluons, which are particles between themselves, and then they talk to each other and bind with each other. I'll go faster. This is even harder to understand. Those of you, I mean many of you would have read in the newspapers, but that is not what I call an understanding. Those of you who have learned about radioactivity maybe in college or maybe in +2 will know that there is yet another interaction which causes the nucleus to break up or to give out part of its nucleons and protons, and that is yet another interaction, and it's called a weak interaction. So these are the 4 known forces. Every force has a mediator. It involves different kinds of matter particles and different kinds of mediators. Therefore, all these interactions are different and they have different physical consequences. I think this part is clear to everybody, and we believe that this is our understanding of what the universe is made of, apart from few more particles that I will come to now in what is going to go on. Is this clear so far? It's clear so far? So, ordinary matter that we all know about, matter that we are made of, contains electrons and quarks, and some mediators between them. Fine? Is this working? Ah, it's working. Okay. Okay, I'll go through this very quickly. Okay. I wanted to give one example of a weak interaction because I want you to try to understand what this weak interaction is in a way that really is kind of playing a big role in your daily life. That is, how does the sun shine? Oh, sorry. Here. How does the sun shine? I think the smaller classes will not know this, but in the maybe in 11th standard, you'll someone from 11th or 12th standard here? How does the sun shine? Yeah, but what is the force, what is the process that is occurring in the sun? What nuclear reaction do you know? Fusion reactions, okay? So it's very simple. We all know protons, right? What is a helium? This is helium, by the way. Helium contains 2 protons and 2 neutrons. So for those in the smaller classes who didn't know it, you know protons, you know neutrons, and helium contains 2 protons and 2 neutrons. What is happening inside the sun is that 4 protons are burning up inside the sun. The sun is very hot, I think all of you know this. It burns up to form helium, and it gives out something else, I don't care, but it gives out some energy which is in some unusual units, don't worry about it. This energy is what we see as sunlight. I tried to put it in some nice bright red. This is the energy from the sun that we see, which is our normal sunlight. Okay? So what has happened is that 2 protons remain the same, 2 protons get converted to neutrons, and this happens in a weak interaction. So this conversion of 4 protons to helium happens through a weak interaction. So you don't think of weak interaction as some scary thing like radioactivity. Our entire solar process, what brings life on earth, is because of weak fusion processes that occur in the sun and give us sunlight. Okay? Now in passing, I just want to mention over here I have put not only a proton and an electron, but I have introduced a new particle. It is called a neutrino. Okay? This neutrino is not something that you will come across until maybe 12th standard or in college, but you can see that this neutrino doesn't have electrical interactions or magnetic interactions. It doesn't have strong interactions. It has only weak interactions. So it's very hard to study this, and there's a lot of effort around the world to study the nature of this particle called neutrino. Okay? It's called neutrino because in Italian that means little neutron. And neutron is a neutral particle. So this is a neutral particle, that's why it doesn't have electric interactions. It doesn't sit inside the nucleus, it doesn't have strong interactions, it has only weak interactions. But let us move on with our story. So now I want to write, I don't want to say all this, I only want to show this. Okay? So what we have done is, just like you have a periodic table of elements, right, from hydrogen onwards, hydrogen, helium and whatever that you learn, we have now what is called a periodic table, or a standard model it is called, of elementary particles. So what does elementary mean? Elementary means something that is simple. And in physics, when you say something is elementary, it means you cannot chop it up further. It's the simplest object which you can study at that level. Okay? You cannot break it up further and study any component parts of it. So elementary is like an electron. So proton is not elementary, but certainly quarks are elementary. Okay? So this is, I'm sorry for the quality of this, look good on my screen. Okay, so first of all you notice that there are 1, 2, 3 rows, okay, columns, sorry, 3 columns. Now what makes up ordinary matter is this. There are 2 quarks which are called up and down type of quarks, and these quarks form protons and neutrons. Then there is the electron which goes around the nucleus, and we saw in the sun that always the electron came with the neutrino. So ordinary matter in our universe is just simply made up of the first generation. These are actually heavier copies of this. This is called charm. It's a heavier version of the up quark. Strange is heavier than the d quark. Muon is heavier than the electron. I'm just reading out the names in case you want to, you're curious about it. This is called top and bottom. See, up and down becomes top and bottom. Sometimes physicists don't have originality. Okay, these are 3 neutrinos which come with the 3 leptons, which are called electron, muon and tau. So mu and tau are simply heavier versions of the electron. You can actually replace the electron and put a muon and make a muonic atom. Why they exist in the universe, we do not know today. Is there a 4th column? We do not know today. Okay? The reason for the existence is a mystery. There are many open questions still in particle physics that maybe some of you who have interest in physics will grow up and start researching on. Right now, this is the status that we have, we don't know. And here on this, in the blue color, the photon, that is the gamma is the notation for the photon. These are the force carriers. This carries the information on the electric force, I said, right? It mediates the force between the electron and the proton. Gluons mediate the forces between quarks to give strong interactions, and W and Z mediate the interactions between all these particles to give weak interactions. And the mediator of gravity is called graviton. It has not yet been found. Fine? So this forms our particle listing, but there is still one particle that is missing. This is in fact the Higgs boson. How many of you have read about the Higgs boson about 6 months ago when news about it first came up? Can you raise your hands? Okay, fine. So about 20% of the audience. Okay, fine. So at this point, everything seems complete, everything seems nice. There are particles and there are interactions, right? So what is it that this Higgs boson does? Why did it cause so much excitement? And I would urge you that all those who have internet connection should go back and read about this Higgs boson, because I am only going to talk a little about how it was discovered, okay? This Higgs boson actually is something, so okay, on the right hand side, I have given you a kind of a, how you can model an interaction. Here is an electron, here is a proton, they are going merrily along, but then a photon exchanges between them and tells, you can bind together in a hydrogen atom. So simple notion like this, okay. This is the way you model these interactions, fine. And then physicists can put a lot of mathematics on top of this number and then do some more research with it, okay. So now I come to what is this Higgs boson, how it was discovered, okay, and why is it important. So we have this list of particles, okay. Now I told you that this column is heavier than this column is heavier than this column, and so on. Again, I am telling some lies here, this is not exactly right. In general, the second generation is heavier than the first and the third is heavier than the second, and so on. What is it that decides how heavy these particles will be? In fact, what tells you, we know that the electron is much lighter than the proton, right? We know that the electron is 1800 times lighter than the proton, right? So what causes different particles to have different masses? And what is it that we know about mass? Who remembers the definition of mass? Tell me. Force that you can apply?
Mass is basically a force you apply on a place or anything.
That is weight, I think you're talking about, right? Weight of the body is like a force, right? What is mass itself? Mass cannot be created or destroyed, okay? That's again half a lie. Okay. But what is, you would have learned, no? Mass is the amount of matter contained in the body, right? Isn't that what you learn in your science textbook in, I think, 6th standard, right? Huh?
The amount of matter contained, the amount of matter contained in the body is called mass.
Yeah, exactly. The amount of matter contained in the body is called mass. This is what you would have learned in your school. And I'm sure none of you understood this definition, right? I never understood it when I was in your class. So the notion of mass, what is the meaning of the amount of matter contained in the body, is something that is very, very, very hard to actually quantify. Okay? So it is something like saying, okay, the amount of matter contained in it is the mass, and then you say that the mass is so much. Now I take some object and say that its mass is, say, 100 grams or something. Well, this is the weight, but okay. So I can convert that equivalently to some mass, right? I know that this has some mass. But they are just interchanging each other. So what is this notion of mass, and why is it that different fundamental particles contain different mass? What is the origin of mass? Now this actually has a very technical and long story behind it, which I don't want to tell you all. What I want to tell you is the following. Scientists have made a lot of models, right? So when you understand a particle and you understand its interaction, you make a little model out of it, like Newton's laws, right? Newton's laws tell you how a particle goes from point 1 to point 2. Like that, you have more and more complicated laws for all these forces. What physicists found out was, if you write all these laws to describe all these particles, you either cannot give any masses to any of the particles, or even if you want to give a mass, you have to give the same mass to all particles. So there is a difficulty over there. So it's a very technical reason. You may not understand why it happens, But there is a problem with giving masses to these particles. It turns out that the theory is inconsistent if you try to give different masses to different particles. Okay. So then the way to give masses is to go the long way around and to give the mass in the form of an interaction. So what have we understood so far? Protons and electrons interact with each other by exchanging a photon, right? And that gives you the electric interaction which forms the atom. So the whole idea of masses of these particles, not all of all these particles that you see over here, okay, photon remains massless, but others, okay, let's just take this block, this 3 by 3 block. These particles get masses through some kind of interaction. So mass is not what is originally something that is the property of this object, like its charge, right? I know that this has a charge, this has a charge, electron has negative charge, for example, but its mass is something that is determined by interacting with some other particle. So if I say this mass is coming by interacting with some other particle, I must first find that other particle, right? Only then I will believe this model. This other particle is called the Higgs boson, and it was named the Higgs boson after Professor Higgs, who first said that such a model should exist. There are actually, this is my mistake, there are actually another 6 people whose photographs should have been put, but I didn't want to confuse anyone here. So this is Higgs and this is also Higgs, okay? Fine. So I am only going to put one slide down on what is this Higgs boson, okay? So forget about the word field, sorry. Those are the lies that I have been telling and it caught me up in this slide, okay? There is a Higgs particle, okay? So this Higgs particle is like the photon. What did I say about the photon? Suppose I blow up the atom, I have a proton over here, I have its electron partner in Bombay, and the photon keeps exchanging, so it goes from here to Bombay and back again and keeps exchanging the information about the electric force. Just like that, actually it turns out that the whole universe is filled with this Higgs interaction, okay? Like, by the way, that photon, when that light ray comes to you, is called a photon particle. When it's interacting between all the charged particles in the universe, it's called a photon field, okay? Same way this is called a Higgs field, but don't worry about that name. The whole universe is filled with that Higgs field. And what are particles like? This is the closest analogy I could get. This is very technical material. I am trying to bring it down to a level which you can understand. Think of a ship on an ocean. One ship is an electron ship, one ship is a U-quark ship, and so on. There are neutrino ship, there are different types of ships, okay? Each ship is made differently. One is made with wood, one is made with very smooth steel, one is old and breaking apart. So all of them have different resistance to the water. Some can go very fast, some get dragged down in the water. So each one of them, therefore, because the sea of that it is floating in is the Higgs field. So all of them have different interaction with this Higgs field, and therefore they all have different mass. So this is the understanding, or this is the qualitative understanding of how this Higgs particle is giving different masses to different particles, because it drags down the different ships in different ways, okay, because the shape of the ship or the material it is made of, all of them are different. It is a very qualitative kind of analogy, okay. Because of that, all these particles have different masses. What about the Higgs particle itself? Higgs particle is like the waves of the sea. So how does the sea interact with itself? It forms waves, and these waves can interact with each other or with itself, and the self interactions are all called the Higgs particle itself. So what they have found last year finally is that when everything else was in place, this was simply something that people said we have not yet found, but we believe that particles get masses like this. Now actually last year in Geneva and CERN, they found an interaction which they believe is the interaction of Higgs particle with like electron, WZ and other particles that I showed you in the previous transparency, okay. So I want to spend the last, I have another 10 minutes, right? Timekeeper's gone, okay. Okay, maybe since I'm now going to move to something different, it's okay so far, right? So the basic understanding of physics for high energy physicists, for particle physicists is there are fundamental particles and there are interactions between them. These interactions always happen by exchanging other particles which are called mediators, like the photon exchanging between electron and proton to give you a physical consequence. For example, atom formation, the whole universe itself is formed to give strong or weak interactions and so on, okay. But all these particles have different masses, and it turns out that in this theory you cannot give different masses to different particles. So then you say that the mass itself is like an interaction with a new particle, and it's complicated because of some technical reason, but finally this new particle has been found. So this is the story so far. So I want to now say, how was this particle found? I want to tell you how people do research in this kind of area and how really large scale all these processes are. So we know that nothing can travel faster than the speed of light. You can keep going faster and faster. When you walk, the car or bus can easily overtake you, and the plane goes faster than the car, but there is a natural upper limit to the speed with which any particle can go, and that is actually the speed of light itself. Nothing can go faster than light when it is traveling in vacuum. So this velocity of, the velocity of light is called c. So the maximum speed or velocity with which you can travel is c itself. So we are traveling with very, very small velocity. C is very, very large. It's about few times 10 power 8 meters per second. Really very fast. So you can, if you know what 1 nanosecond means, the light particle travels 30 centimeters in 1 nanosecond. Like it's about a foot, right? So in 1 nanosecond it's gone from here to here. It's really very fast. So what this is the CERN accelerator in Geneva, which is in Switzerland. Actually it's halfway between Switzerland and France. So what they do is that they have these circular objects which are called accelerators. And in each stage they keep accelerating the particle more and more. And finally by this time we have a 27 kilometer ring, okay? 27, the distance from here to the airport is about 15 kilometers. So you can double that is 27 kilometers over here, okay? By that time, the velocity that has been reached, the proton which is being accelerated here is 0.999999 times the velocity of light, very, very close to the velocity of light. So this whole thing is a very huge technological challenge, and this entire accelerator is cooled down to minus 271 degrees. Right now this room is cooled to about plus 23 degrees, and that is cooled to minus 271 degrees, and actually in the universe you cannot cool below minus 273 point something degrees. So we are very close to absolute zero of temperature over here. And okay, what it does is that they have put, you can see the one blue line which is a proton going around, a red line which is a proton going around in the anti-clockwise direction on this side, and at some points these two particles are made to collide with each other, and there are 4 experiments there with strange names. You don't need to worry about it, okay? And this is the example of that detector that I showed you. For example, this Atlas or CMS detector looks like this. The CMS detector looks like this. Doesn't matter what this is made up of, but this is the human being that is standing beside. So you can understand how large these objects are, right? Can you see the human being over here? Okay, so compared to that, the size of these detectors are, this is not any science lab experiment, these are huge labs with humongous size detectors, and it's really a marvel of technology and science, not just science itself. So what happens is that, the reason you have this is that in the center the two protons collide with each other and produce huge numbers of particles. So here in this part you can see electromagnetic. So all the electromagnetic particles like electrons and the photons are detected over here, and here hadrons means all the protons and stuff are detected over here, and here are the muons which need a long path. If the muons are like heavy electrons, they were all detected over here. So you detect all the possible particles that come out, and then you go back and say what kind of physics could have produced these kinds of signatures. And the challenge that you have is that you have 40 million collisions per second. You don't have just one proton colliding with another proton. Every second 40 million of them are colliding, and you have some 1 billion interactions, and then you can imagine the amount of okay, all of you are now familiar with computers. There is a memory on the computer. You can store your files over there, and there is a certain size of your hard disk, so many megabytes or gigabytes of data, and you can see that this is 15 million gigabytes per year of data is produced in these collisions. You can, if you put it in CDs, you will get a 20 kilometer high stack of CDs per year. And this is the kind of data that they are analyzing. So you can see that it needs technology, it needs electronics, it needs computers, it needs physicists, and it's a very, very amazing thing. And then in all this, this is how the tracks look. So in one collision, it literally looks like it has blasted apart and formed something like 3,000 collisions, and in the yellow are all the tracks of all the particles that have been produced in this collision. This is in the ATLAS experiment, and the other one is in the CMS experiment. And you can see that the longer ones are the muons and stuff, doesn't matter, okay. And then in all that they have searched and found, they have in all this they go through painstakingly event by event and say, is there one of these interactions which was caused by producing a Higgs particle? And they have actually found such events, and they have said, yes, now we have found the Higgs boson. We are confident up till, very good confidence level that this is the Higgs, but the experiment is going on, and they are going to confirm many more details of the Higgs later, okay. So this story of the Higgs ends over here. I want to just end by saying, okay, so is this our understanding of the universe? And the answer is the following, okay. Whatever our interactions that we had, our model, like this is what I call the periodic table of elements became the standard model of particle physics. This has been completed by finding the Higgs particle. However, in the last 10 years, lot of experiments have come up which are surveying the sky. So this is not only our own galaxy, galaxies nearby. In fact, things like the age of the universe. Do people know the age of the universe? Maybe you should think about it. How old is the universe? That is also known today, okay. But they found out that really our ordinary matter that we thought about, the protons, the neutrons, the electrons, that we thought is making up the entire universe, is actually only the light blue part of the universe, okay. So the ordinary matter that we know comprises only the small 4% or 4.6% of the matter of the universe. Another 25% is green, which is called dark matter. This has been observed, but we don't know what it is made of. It is certainly not made up of protons, neutrons and electrons. What could it be made of? What kind of interactions could it have? Are there some new interactions beyond what we already know? Are there new particles beyond what we already know? And finally, this huge amount of 72%, the whole universe is filled with something called dark energy. We don't even know if it has a particle-like nature. Is it like particles like electrons and quarks? Is it something else completely? Actually, scientists have no clue, okay. At least dark matter you think can be made up of particles, but dark energy you have no idea. So the whole origin of the universe, okay, this forget about, okay, is now, and what the universe is made of, we have now completely understood really only 4.5%. It is a huge amount still to learn, and I hope you can read this. Unfortunately, it seems to have gone out of the thing. This story is fascinating to scientists. I think it should be fascinating to everybody, because it is the story of the only universe that we have ever known and ever will know, I think. Thank you.
Thank you so much, Indu. Amazing talk. Questions? Come on, you.
Yeah.
And so is the Higgs boson. Are they related?
Okay. Nice question. So there are two different things. If a particle has mass, it will experience gravitational interaction. How did that mass come up in the first place? Through interaction with Higgs. Is this clear? So the two are different. If there is no interaction with the Higgs boson, for example, a photon, right, has no mass, it will never interact with the Higgs, it will never acquire a mass, it will also therefore not interact with gravity, okay. But, okay, again I am telling half a lie, okay, over here, so I don't want to, let me not answer it this way. Forget the photon, because I don't want to go to general relativity, sorry. Let me leave the answer as this. If a particle, okay, I will leave the answer as it is, but it is only half correct. Okay, so the Higgs gives masses to particles. Okay, actually, since this question has been asked, let me clarify. I didn't want to go into these details, but maybe I don't want to leave any confusion. When I talked about Higgs giving masses to particles, it is these fundamental particles, the electrons, the quarks and stuff like that. Actually, even Higgs doesn't give mass to protons, because what happens is that the quarks bind together through strong interactions to form protons, and the bulk of its mass actually comes from that interaction, from the strong interaction. But how does the quark itself get mass? That is coming from the Higgs. How does the electron itself get mass? That is coming from the Higgs. Is this clear? And this cannot be switched off, because the Higgs field has been there from the beginning of the universe. So every particle has a certain, that's what is there in the textbooks, right? It's certain property of it's that matter, amount of matter contained in the body cannot be changed. An electron will always have a well-defined mass. Once it has a mass, it will interact with gravity, okay? Now that second statement is an approximation. The first statement is exact. Okay? Yeah.
There are 3 generations of neutrinos
Who is speaking? Can you raise your hand? Okay, yeah.
associated with electron, muon and tauon. So being chargeless, massless particles, how do we distinguish between these 3 generations?
Oh, a very nice question. Sorry, I think the students will not be able to get anything out of this. The question was there are 3 different types of neutrinos, all are chargeless, right? But you can see that I was very careful to write nu sub e, nu sub mu, nu sub tau, okay? And the way you distinguish them is their association with their partner, what is called leptons. So for example, electron and electron neutrino are like, were together in one generation, muon and muon neutrino were in one generation, tau and tau neutrino were in one generation. So if you see in the, I had an equation for the sun, right? So you can see here, okay, doesn't matter since you are old enough to understand this, there's a positron, okay? So the positron and the neutrino will always come together, so electron and electron neutrino are always coming together. So this is how you will distinguish the different flavors. So with the muon you will get the muon neutrino. So now if I put the positron on this side of the equation, it will become, antiparticle will become particle, right, electron. So if I start with an electron interaction, I will only get nu e. If I start with a nu mu interaction, I will only get nu mu. So you can ask the other question, suppose I start with a nu mu, will I get an electron out of it kind of thing, right? So that is the way you will distinguish the different flavors.
Other than that, there is no physical distinction.
There is a huge amount of physical distinction and it is an entirely different talk. It is the study of neutrinos. As I said, there's a lot of, by the way, there's a plan in India also to study these neutrinos. It is called the India-based Neutrino Observatory. It turns out that these nu e, nu mu, nu tau are not physical particles. And actually mixtures of them are physical particles, and this is called neutrino oscillations. And so the whole picture gets really confused, but it's very interesting and very fascinating. And it's so therefore the other lie that I told, that neutrinos get masses from the Higgs boson, may not be true. It's possible that neutrinos may get masses from a different mechanism. Okay, as I said, see, at every level we are making approximations, and for a mixed audience I have not clarified. So the statement is that yes, different flavors will act differently. Neutrinos and antineutrinos are different, even though both are neutral. That has been confirmed, because what comes out in the nuclear reactor is antineutrino, and it will not interact in the same way with the detector as neutrinos which are coming from the sun. This has been established. So we know nu e and nu e bar are different, okay, and we know that nu e, nu mu, nu tau are different, but from a little different way, because those are not the physical mass states, okay. So sorry for the complication. I hope the others were not listening, okay.
One doubt. In the newspaper it was given that
Can you just raise your hands? I can't see who. Okay, yeah. Okay, newspapers write a lot of things, okay. in the sense that, okay, very quickly, very early, okay, the Big Bang is what created the universe. That is what we believe, right? And when the universe was begun, from that time the Higgs boson should be there at the time when all these particles were formed. So from the start of the Big Bang to when these electrons and quarks were produced is a very, very short time. So in that sense, from the time of the Big Bang, but actually the Higgs boson has nothing to do with the Big Bang, okay. So see, newspapers cannot give technical talks, so they have to tell different kinds of lies. As I said, you know, they're just not lies, they're just approximations in order to give a context to the discovery, okay.
Questions anymore? Upstairs perhaps?
Yeah, yes. You'll have to shout a little, I think, but I think we can hear you.
This Big Bang theory is based on the God's particle.
See, God's particle is what the public like to call the Higgs boson, right? So Higgs boson is simply a particle. I mean, whether it's God, I think. No, that was the question that was asked downstairs, right? What is the relationship between Big Bang theory and Higgs boson? There is none. No, that's what I said. A lot of newspaper spin has happened on this. So Big Bang is Big Bang. This is how we believe our universe was produced. And then the universe went through a period of inflation and then produced some set of particles. And among these set of particles are these fundamental particles that we are studying. And so from that time on, they always had to have that mass. And this mass comes from an interaction with the Higgs. So the Higgs had also better have been there from that time. That's all. It has nothing to do with actually the formation of the Higgs. Or sorry, formation of the universe.
Yeah. So final question. Yeah.
In your last slide, there was these two pie charts with the amount of matter and energy in the universe.
Yeah, keep going. I know.
So in the left one, there is dark energy consisting of 72%, but 13.7 billion years ago, that was not there. Where did it come from? Where did the dark energy start from?
13.7 billion years ago, it was
it's
not
there.
there.
There's no dark energy in that pie chart. Where did it come from today?
See, the dark energy is not matter, okay? It's a parameter in the evolution equation of the universe, okay? So, all it says is the following. Maybe I should try to, let me see how much I can say about it. Suppose the parameter was not there. The universe will just be expanding like this, okay? So, this parameter can be 0, positive or negative, okay? So, you know the universe is expanding. So, whether the universe is expanding uniformly like this, whether it's expanding slower and slower and slower and will come to a halt at some point, or whether it's going boom apart, that means its expansion is accelerating. That is what this parameter actually does. Okay, so it's telling you that this the value that you measure today is showing that the universe is not only expanding, but the rate of expansion is accelerating. So obviously it had to be smaller earlier. In 13.7 billion years is the age of the universe. I didn't realize that was there in the chart, but whatever. So when this acceleration happens, obviously this parameter becomes larger and larger and will be largest today. So that means you know that when something has to accelerate, there must be some energy or dynamics which drives that, right? So what is driving that? We have no clue. That is what I'm saying. We don't know what this dark energy is and where it's coming from. At present, it's a parameter in the equation, in Einstein's equation. So yeah.
Okay. Thank you for the questions. Thank you, Indu, so much again for the talk. Before we go to the break, a couple of quick announcements. Those who have not taken the registration kits, please go and take them. The counter will close in another 5 minutes. Second is that the people who are participating in the quiz prelims, some of you please go to room 423 and some of you please go upstairs. The rest of the people who do not want to participate in the quiz, please stay downstairs for the Grill the Scientist session. This is after the talk, after the break. Okay, so this is at 12:30. And okay, so the thing is that the quiz level, it is pitched at class 8 and above. Okay, so if you're coming from class 5, 6 or 7, you might find it a little difficult, but you know, please give it anyway. So the quiz.
Sorry, I don't want you to see. We had the kind of written to the school saying that we expect students from 8th standard onwards. So I think all of you are welcome to write the quiz, but you must be prepared that you may not know much of the stuff over there because we did aim it at 8th standard and above students. So you can decide whether or not you want to participate in it, right? I mean, please think about it. I mean, and I don't want you to be disheartened if you find you cannot answer the questions because then it was really meant for some older students, okay? Thanks.
And finally, those who do want to participate in the quiz, could you please raise your hands? We want an estimate. Okay, thank you so much. Yeah, so quiz, you'll be directed where you have to go after the break. So please, outside there is snacks, tea, coffee, other things. Please go and have them. Come back here at 11:30. And those who want the quiz, please go up to 423 or wherever you're directed.